John Mater es un astrofísico y cosmólogo estadounidense, galardonado con el Premio Nobel de Física por su trabajo en el Explorador del Fondo Cósmico, conocido como COBE, junto a George Smoot. Con los datos obtenidos por este satélite espacial, se confirmó la teoría de expansión del universo desde el Big Bang. La Universidad de La Laguna le ha otorgado el doctorado honoris causa para reconocer sus vitales contribuciones en el avance del conocimiento del espacio.
I got interested in the cosmic background radiation and the early universe in several steps. In college, I read about the expanding universe and I heard about it. The cosmic microwave background radiation was discovered while I was a student. And then in graduate school, I thought I would be a theoretical physicist because that seemed so exciting, and relativity and quantum mechanics were great discoveries and very mysterious. But then I wanted to find a thesis project, and they said, "Are you wealthy?" No, I'm not wealthy. Then don't be a theoretical physicist. So I talked to faculty members. Well, what projects do you have to work on? And I found people who have got to try to measure the cosmic microwave background radiation using an instrument on the ground. And so I said, I'd like to do that, and I worked on that. And then, and it worked. And then we said, well, maybe the next step is to build an apparatus to go up on a balloon payload to 40 kilometers up in the sky to measure it better. So I said, I'd like to work on that, and started. And then that project actually did not function correctly, so I got to write a thesis about a non-functioning apparatus, and I got a job for NASA to try something else. I'll become a radio astronomer because this cosmic background radiation is too difficult for a young person. And then NASA said that very summer, well, we want proposals for new satellite missions. So I said, boss, my thesis project failed, but we should try it in outer space. So he said, we'll call up our friends and we will write a proposal. So that I thought that will never work, but it did work. And so 15 years later, we finished the satellite, the Cosmic Background Explorer satellite, and launched it into space, and it worked. So that's how I got started. It seems very accidental and very random, but I think everyone knew at the time that it was a very valuable research project. We just didn't know how to do it at first. So I'm just so thrilled to be a recipient of the honoris causa doctorate because it means to me, not only did we do good work, but it made a difference to you here at the university. So it's a celebration of the worldwide connection of scientists and the importance of our work for everyone. Well, for me, it's a celebration of friendship with Dr. Beckman because I've known him for a very long time, and we worked in a very similar path. He was there first. He was a young faculty member in England while I was a graduate student in Berkeley, California. They started work on the ground, and then they built their balloon payload, and I started to work on the ground, and we built our balloon payload in Berkeley. And we've been aware of each other's work all this time. Then I didn't know at the time, but Dr. Beckman also worked on satellite mission proposals, so he could have been there first. But we all have different luck, different places we're starting from. Now we compare notes and tell stories, and John is continuing to work in fundamental research. And there's a major research group here at the Institute of Astrofísica de Canarias to measure the cosmic background radiation even better. Well, I'm not familiar in detail, but I know people here have been using the Webb telescope, which I worked on to help make that possible. The people are publishing research results from the Space Telescope. So it's a very powerful team here. I'm particularly aware that we have telescopes very nearby, and building the equipment and making it work correctly is very important because the the volcanoes give us the right spot to put a great telescope. Above most of the Earth's atmosphere, above much of the weather, and high enough that we can get a clear view. So it's one of the prime sites in the entire world for putting a telescope. So we need to have engineers and scientists working together to build that equipment, because that's part of the process here too. Well, for me, the Cosmic Background Explorer, or the COBE satellite, was a very personal creation. It was my idea that we should build this, and then we recruited many people to join. I was the head scientist for the project, and so I was participating in all of the analysis of all of the equipment, all of the scientific results, and so it was very exciting for me to see something that was my idea to grow up into a whole satellite and be launched. And then we see afterwards that we've started up a new subject, what was called the era of precision cosmology, as the Nobel Prize Committee said it. So when we started, almost nothing was known. We had an alternate theory of the early universe. It was called the steady state theory, and it predicted different things. And as soon as we got the measurements back from the satellite, we knew that other theory was wrong, although a few people never did agree with that. Anyway, because we measured the pattern of the hot and cold spots, the anisotropy, we were able then to start building what we now call the standard model of the expanding universe. And we're able to measure the parameters within a few percent. How old is the universe? How rapidly is it expanding? How much matter is there? How much, that is to say, ordinary matter? How much dark matter is there? How much dark energy is there? And what is the temperature, of course? And all of these things have been measured extremely precisely now, far beyond anything that we ever could have imagined when we started proposing the satellite in 1974. Well, I knew right away that my world has changed a lot because I now have new duties. I'm a spokesman in the world for our project. Everybody wants to know more about this scientific research, and that was one part. The other part was I'm so thankful that the work of our team has been recognized. So 1,500 people built and operated and analyzed the data from that project. So we've all been recognized. So it was a recognition for everyone, for two of us to receive the prize. Well, the Webb telescope was launched, as you know, on Christmas morning of 2021. After over 20 years of preparation. It's an extraordinarily complex project with a telescope is 6.5 meters in diameter. It's much larger than the rocket. It is protected by a huge umbrella, a huge sunshade that's as big as a tennis court, and that had to be unfolded after launch. So there were hundreds of different ways it could have failed when we built it, and we knew that we just had to be very, very careful. So the first thing to do after it's launched is to unfold it and prepare it for operations. That took us 6 months. And then right away, as soon as we got it focused and could take pictures of the sky, we saw immediately that our objectives were fulfilled. Number one, please see as far back in time as you can. See the first galaxies growing from the primordial material. So we didn't know exactly how far back we would see, but we've now seen a galaxy that was formed 290 million years after the Big Bang, or we see it as it was then already. Maybe it was even formed before that. So we've seen some of the very first objects. We've seen some great surprises. It seems that those early galaxies are bigger and brighter and hotter than we thought they would be. It seems that there are black holes. Almost every galaxy has a black hole in the center, millions or billions of times the mass of the sun. We do not know how that happened. And we've seen some very far away in space, very far back in time, and we don't know how they could be so big and so bright so soon. So perhaps some of them were formed in the Big Bang itself. That would be a very exciting result, and we're working on that. We don't know the answer to that one. So anyway, those are the two of the big results from the very early times. Much more close to home, we are seeing places where stars are being born today. And stars, presumably like the sun, are born in clouds of dust and gas. So we were able to see inside these clouds because we're using infrared radiation. So we can see inside the dust clouds where stars are being born. And we see them shining out with their own light. Also, by the way, some objects are too cool to emit their own visible light, so we can see objects that are much colder than you and I. We see them in a new way. We see the debris from stars that have exploded. This is part of our story also. Stars do explode when they're old. Some of them make a great supernova and a huge flash. It may be as bright as an entire galaxy for a few months. And many of the chemical elements that we see around us, the carbon, the oxygen, the nitrogen, all the beginning of the periodic table, those come from stars that explode. And of course, we wouldn't be here without them. So you and I are exploded stars. We've been able to confirm that many of the very heavy elements are formed inside neutron stars. Now, a neutron star is what happens when a star gets old and burns out almost all of its fuel, and the remains can shrink down to a diameter of about 15 kilometers, size of a city, gigantic atomic nucleus. So if something can happen to that, so it explodes again, then it makes the heavy elements, all the uranium and the gold and the lead and the other things that are very heavy, are performed in that kind of process. So that's something we've been able to confirm with the Webb telescope. Yeah, and then closer to home, even closer than that, we're looking at planets around other stars and satellites in the solar system, where we are, of course, very interested in could there be life somewhere else? Honestly, we do not know. It seems to either life will never happen, or life happened exactly once here on Earth, or life happens many places and we just don't know the answer. So and just if it's possible for life to occur elsewhere, then we should look. So how do you look? You look for things that would be, say, in the atmosphere of another planet. You'd like to know if there's oxygen, because here on Earth, oxygen is made by plants and algae. If you could find that in the atmosphere of another planet, you would say, that's a clue that maybe it's alive. Well, we can't do that yet. It's too hard, but we're practicing. So what we can do is, if this is a star and here's a planet, and then the planet goes between the telescope and the star, and you see the star will blink, get a little fainter for a while, because the planet is blocking some starlight, then sometimes we can able to measure the light that goes through the atmosphere of the planet on its way to our telescope. So now we can do a chemical analysis of that light and see if there are molecules in the atmosphere of another planet. So we're doing this, and we have many hundreds of planets that we can observe this way. Now, none of them are like Earth, but they do confirm that method works, and so they're pretty, planets are pretty different from what we have in the solar system. So that's one of the major results. The other planetary systems are very different from ours. Maybe that means that life on planets like Earth is rare, but we really can't tell you yet. Here in the solar system, the planets, the outer planets, have moons, and those could be alive. Everybody's heard about the possibility of life on Mars, and we've been observing that with the Webb telescope. I don't know of any great surprises there yet, but we do have surprises for the moons of the outer planets. Jupiter has 4 very bright satellites that were discovered by Galileo in 1609. And another even stranger place is called Titan. It's a moon of Saturn. It's the only moon in the solar system that has enough atmosphere to have weather. So Titan is very cold, so that it has lakes, it has rivers, it has clouds and rain, and made out of ethane and methane, so hydrocarbons. And the surface of that one is ice. Probably under that is an ocean, very far down. So this is another fascinating place to look for signs of life that could be very different from here. So we actually have already landed on the surface. The Cassini mission, and it had a probe called Huygens that landed on the surface. We NASA are sending one, have already prepared it. We will be sending one to land on the surface of Titan. And it will have a quadcopter that will fly around on the surface to look for things. So I don't know what we're going to find, but it's just a reminder that the solar system is a very exciting place to look. I think it's possible. We know what astronomers would build. They would build a telescope that's better than the Webb telescope to look for, actually be capable of measuring an image, see a little image of the Earth moving around its star. And then if you could do that, you could analyze its atmosphere to see does it have oxygen. So right now our tools are not good enough to do that. The Webb telescope can't do it. It was not designed for that. But we know what to try. So that would be one way. I've been working on a thing called a star shade. If you could cast a shadow of a star onto a telescope, then you'd be able to see better because the star is so much brighter than the planets, and it's very hard to see a very faint planet next to a very bright star. So that's a star shade idea. And there's even an idea about how to use it with a telescope on the ground. So there's a European extremely large telescope being completed in Chile. It's huge. It's 39 meters in diameter. It's much, much bigger than anything we are likely to have in space for another century. So if we can use that with a star shade, then there's a chance to see those planets very well. So there's that. There's also, of course, here in the solar system, we have the ability to eventually bring home samples of rock from Mars. So I think there's a reason to think that Mars could have been alive. We know that it had water, it had lakes and rivers and weather. It's pretty dry now, but there's water underground. So it might even be that there's life underground today. So if we could find the right samples and drill deep enough, we might be able to bring home a sample, say, look what I saw. Mars is alive. That's not impossible. So in our lifetimes, it's possible. Good question. Right now, we're having a political upheaval in the United States, and I don't know how that's going to turn out. The plan that we did have was very dramatic, very glorious, and we have many ways to advance science. So if we get to do what we wanted to do, then we would continue building great telescopes. The U.S. is finishing up a telescope called the Nancy Grace Rumman Space Telescope, and which would be launched in 2 years. And we'll survey a large amount of the sky, looking for very interesting infrared light and searching for evidence of dark matter and dark energy. We are also finishing up a telescope in Chile called the Vera Rubin telescope, which is going to survey the entire sky every 3 nights, looking for things that change. So we have ambitions for other telescopes in the future, but anyway, that's what has been started, and I think it's wonderful. I hope we get to continue it. Yes, well, quite clearly international collaborations have worked very well for NASA. We like to invite other nations to participate because we also like to make our data available to the entire world. So the Webb telescope and the Hubble telescope are available to every astronomer everywhere. Write us a proposal. If it's a good proposal, we'll do it. And we make sure that we don't even know who you are when we read the proposal. It's based on the quality of the proposal, so graduate students can win. We like that, and so I think it's a good arrangement, and I hope that we're able to continue it. it seems to me that there's so much that's possible now in scientific research, that we have new tools, new ways of thinking. Artificial intelligence is helping us as scientists to at least do the ordinary routine kinds of things that a robot can do for you. So many new things are possible today that have meant we're beginning to do them. When in the United States, for instance, every 10 years we write a scientific report about what are the great priorities that we should do in astronomy. And the plan that you can see there will probably take a century to accomplish. So we have at least 100 years of good scientific work in front of us. So I think it's there for us to do. We need to find ways to do it because we have to actually, the people that do it have to be paid so they can eat and buy their equipment. And so that's part of the process. But here, of course, the practical effects of science are also very numerous. We study pure science in school, and then most of the science students go off and they do something a little bit different. We don't all become research scientists. We help, we build engineering projects, we work in finance, we do all kinds of other things. So a scientifically trained student will always have a job.